Come on in, everyone. Only four of you so far. Hey, Andre, are you in my 241 class too? I don't know if you're talking, but you're muted if you are. While we're waiting for other people to log in, does anyone have any questions? Feel free to ask them now. Oh, man. Gotcha. Thanks, Andre. Yeah, it's just weird. I just came out of 241 and I swore I saw your picture up at the top, but there might be another student that, you know, maybe has the same hair color as you, and that's it. That posted their picture. I'm really horrible at recognizing faces with names, so I apologize in advance for all that. All right, we're up to 8 people in the class now, so that's a little better. I'm feeling pretty good about that. When we last met, we were talking about temperature scales. I gave you the Kelvin scale, I gave you the Celsius scale. I also introduced you to the Fahrenheit and uh, Rankine scale. Showed you a way to convert units within that. I didn't get a chance to. Well, I did talk about the atomic theory of matter and how the unified atomic mass unit, what we call lowercase u, is actually, if you want it in kilograms, it's one divided by parentheses 1,000 times Avogadro's number, close parentheses. If you want it in grams, it's one over Avogadro's number, and that's it. So you don't have to learn another number. In other words, that's the main thing. And I wanted you to understand why that's the case. That it's done that. You actually might. I got a little mixed up when I was working on your class, but the class I did, I think it was last night. I did a much better job. So if you will look at the Tuesday nights class, I think I did a little better job helping people understand why U is one over Avogadro's number. So definitely check that out if you want to. That video has been posted as well as your last class video has been posted. Everything's been posted so far today except for uh, the lab I had this morning for you guys. I think that's already been posted, but the lecture I just made in 241 hasn't been posted, and this lecture won't be posted for another couple hours, but pretty soon it will be. Anyone have any questions on the stuff so far? I did make the homeworks available. Hopefully, y'all have all been able to at least see those. I have had some students ask me about fixing due dates. I tried to erase all the due dates, to be honest with you, within the Canvas stuff before it was imported into the current course. That might have worked, it might not, but currently the only thing, and probably this will be the way the whole semester, the only dates that will be correct on the Canvas side will be dates of chapters that I've already covered or in process of covering. So right now we're in chapter 17, and I doubt there will be correct dates for anything for chapter 18, for anything for chapter 19, so on and so forth. But I'll try to keep it up to date. On the day we start a chapter, I'll try to set all the dates associated with that chapter correct. So just keep that in mind. We now have 11 of you in here, and I was telling you how we had started chapter 17, which is temperature, thermal expansion, and the ideal gas law. I wanted to go ahead and show you an example of how we could make use, for instance, of this new atomic mass unit. So, for instance, here's the first example I'm going to go with. I got to show you. Uh, I'm going to show you my screen. First, I got to turn to the right page. Somehow this thing always jumps to, oops, wrong one. No wonder. Okay, now I'm right. All right, I'm going to share my screen, but for some reason, like I said, this thing always jumps to like 1,000 pages ahead or whatever. It should be coming up in a second or so. I don't know if you guys have been noticing lately, but there is a company called Granger that I occasionally order stuff from online. They're a supply company. They supply sort of industrial supplies, so you can buy like uh, metal to be used for welding or whatever, various other things as well. But they have a really wonderful website for their periodic table. So just to let you know, that's a decent website. What I'm going to do is I'm going to use the fact that the density of copper is 8.9 times 10 to the third kilograms per cubic meter, and that its atomic mass on from the periodic table is just 63 roughly. And I'm going to use that to estimate the spacing between the atoms. So given, whoa, Nelly, I'm writing with the wrong thing. The person come in. Given that the density of copper is 8.9 times 10 to the third kilograms per cubic meter, and the mass per atom of copper is 63 U per atom. Determine the distance between adjacent atoms. So this is specifically for the density given, which means it's for the specific temperature that that density is given, and so on and so forth. So what we want to do is figure this out. So we want to try to get an idea of exactly how far the atoms are apart. So what we could do is use the density to imagine basically 1 cubic meter of material. So let's start off like this. I'm going to say solution. What I'm going to imagine is a cubic box, if you will, made of copper. And this box is going to be 1 meter by 1 meter by 1 meter. And because of that, I know that its mass of the copper, actually, I should say copper block, not copper box. Whoa, Nelly. Want to do the eraser and do something else. So the mass of the block is equal to, notice that's a cubic meter. So according to the density, that mass is 8.9 times 10 to the third kilograms. All right. Now I can use that to figure out exactly how many nuclei that there are in there. In other words, how many atoms there are. So if I take the mass of the block and I divide it by the mass of a copper atom, that will give me the number of atoms. So actually, I didn't give myself enough room. Let me do that a little better. So the number of atoms is equal to the mass of the block divided by the mass of copper atoms. So that's going to be 8.9 times 10 to the third kilograms. And this is going to be divided by 63. And that is atomic mass units per atom. But we also know that 1 U is equal to 1.669 0.0605 times 10 to the negative 27 kilograms. Again, you don't necessarily have to memorize that number. All you have to do is do 1 over Avogadro's number and then divide by 1,000. So what you see here is when I do this math, and I'm going to make sure I use parentheses, I'm typing in 8.9 e to the third, and I do divide by parentheses 63 times 1.6605 e to the negative 27. And when I divide that, I get 8.5. And I'm going to carry one extra sig fig. In all honesty, we definitely only have 2 sig figs. So it's 8.51 times 10 to the 28th. That's 10 to the 28th atoms. So notice that's how the units work out. The U cancels out with the U down there in the bottom, and then the kilogram cancels out with the kilogram down there in the bottom, and we're just left with atoms. So there's 8.51 times 10 to the 28th atoms in that 1 cubic meter block. So that corresponds to what I'll call, well, I'll say the number of atoms which is equal to 8.51 times 10 to the 28th atoms. So that's it, and I'm going to give that symbol N. Okay, and what we should realize is that in principle, a cube should be made something like this. So let me draw a small cube over here to get an idea. Oops. Keeps reverting back to a eraser. So there's a square, and we could imagine that it's going to have a bunch of little atoms here like that. And I'm going to say, since they're equal on each side, each one's 1 meter by 1 meter by 1 meter, I should expect that each of those sides would have the same number of atoms down it. Same thing happens here. The same thing happens here, so that I get dot, dot, dot. This would be in atoms. And then not only that, in the third dimension, we'd get dot, 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 dot. This would also be in. So in fact, what we know is 8.51. Let me write it another way. What we know is N, which is equal to 8.51 times 10 to the 28 atoms, is equal to N cubed. So if I could solve for N, that would tell me how many are on that one side, or how many are on that other side, or how many are on that other side. And then I can flip that over, and that'll give me the individual distance between them, because these N's are going to come out to be in the number of atoms in a given meter, so I can call it N per meter. So with that in mind, I'll say N is equal to the cubed root of N, which equals the cube root of N cubed, which equals the cubed root. That N cubed, cube root of N cubed, I just wrote there so you know exactly what I'm doing. And this is how I'm actually implementing the calculation. And again, this 1 is really an extra sig fig. And what we could do is we can convert this to now atoms per cubic meter, because that's specifically the volume over which we did that, in which case this would become atoms per cubic meter. And that'll be a little more helpful in us trying to figure out exactly what we're going to do next. I mean, we already know what we're going to do. I've already pointed it out to you. But by writing per cubic meter, we'll see that this math will come out to be a number of atoms per meter. So I'm going to take that 8.51 times 10 to the 28th. I'm going to raise it to the 1/3 power. because that's the same thing as a cube root. And that gives me 4.3. I might as well call it 4.40 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's atoms per meter. Notice the cube root acting on a meter cubed in the denominator gives a single meter in the denominator. So now I've got 4.409 atoms per meter. And if I take 1 over n, that becomes 2.3 or 2.27 with one extra sig fig, 2.27 times 10 to the negative 10th meters per atom. And that's really what we're shooting for here. So what we found is that the individual spacing is 2.3 times 10 to the negative 10th meters between two adjacent atoms. Anybody have any questions about that? So I think that's a pretty straightforward calculation. It's not easy to motivate the first time you do it, but after you've seen it now, you should be able to sort of regurgitate the same information. You might want to try doing this by looking up the density of, say, titanium and the atomic mass of titanium, making sure you use the appropriate units and see if you can do it that way as well. And there's actually a bunch of different ways you could do it. But the main thing is now we have an idea of roughly how far atoms are apart. In fact, if you've done any studying, you probably already know that atoms are basically hydrogen is the smallest and they get bigger as you go to left to right. But then when you go from one row to the next on the periodic table, uh, that second row is not a whole lot bigger than the first row. And then the third row is not a whole lot bigger than the second row, and so on and so forth. So, in principle, it does get bigger as you go to the right or down, but it's not a huge difference, to be honest with you, between the size of a uranium atom and the size of a hydrogen atom. So that's something worthwhile to keep in mind. But now that we know that's roughly like hydrogen has a radius, the Bohr radius is 0.529 times 10 to the negative 10th meters. That's what the Bohr radius is. And of course, that would give you roughly 1 times 10 to the negative 10th is the actual diameter. So it seems that the atoms, at least in a solid around 20 degrees Celsius, are about 1 atom apart. That's a good ballpark figure. If you do this with a liquid, you'll find a different number. If you do this with a gaseous state, you'll find really crazy numbers. So I invite you all to do that. Try to look up. I wouldn't worry too much with the gaseous state, just because the ideal gas law is going to help us with that. But at least with the liquid state, if you look up, say, the density of molten copper at a given temperature, you might be able to find out what that is. But you could also do it, for instance, with water. You just have to then use the molecular weight of a single molecule of water, which would be the same way you'd normally do the molecular mass of water, twice hydrogen plus one oxygen. Anyways, that will give you a neat little thing, and you'll see that in fact the distances between atoms and liquids is quite a bit larger than the distance between atoms and a solid. So, anybody have any questions on that? All right, there's another thing that they want to talk to you about, and this is something you sort of already learned in chemistry, but it turns out that atoms combine in whole number ratios. And in fact, whenever you find something less than a whole number, that's probably because one of the other atoms that you counted as a single atom really should have been that one, and all the other single atoms should have been two atoms. And then that one that's a half an atom is actually an atom. And you can use things like that to sort of estimate. For instance, uh, here's a good example. For instance, for every gram of carbon that you put into the atmosphere, how many, let's say kilograms, I'm going to write it right here. For every whoa, kilogram of carbon released to the atmosphere, how many kilograms of CO2 can be made? In other words, there's copious amounts of oxygen in the atmosphere. So pretty much a large fraction of all the carbon atoms you emit out of your tailpipe on your gas engine, uh, just about all of them will go to making carbon dioxide. Some of them make carbon monoxide, and some of them make other things. But in generally, the key point is how many of them can be made into carbon dioxide. Uh, that's a neat little thing for you to try. So I'll say so I'll just make that like an extra credit problem. But that's pretty interesting because gasoline. Gasoline's basically a long train of hydrocarbons. It's got other little things in it, but the general idea is carbon, hydrogen, hydrogen, carbon, hydrogen, hydrogen, carbon, hydrogen, hydrogen, and then there's some oxygens and things of that sort as well. But basically, that's what the uh, organic chemistry is focused on, and that's what gasoline is. I will tell you that strictly speaking, there's not really such thing as an octane molecule, but there are things similar to it where you have, say, eight oxygens or excuse me, eight carbons, or some people have even argued that it has eight hydrogens. I don't think that's the case, but anyways, that's not a big deal. But the main thing is when you realize that gasoline is made up of hydrocarbons, so there's a lot of carbons, hydrogens, and oxygen. Uh, the majority of the mass is likely carbon, but then that carbon is turned into a way bigger mass of carbon dioxide. So that's something else you can kind of do by just knowing these things. I think that's basically what I wanted to do with regards to that. Now, what I want to do is mention some things about temperature and how things expand, so on and so forth. You've probably all driven over a bridge and heard it go clunk, 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 or even interstates. You can, especially like 264, that interstate is mostly made of concrete as opposed to asphalt, and concrete isn't quite as forgiving about expansion and contraction. So they had to cut it in blocks, basically, uh, where you have an expansion break every certain distance, so that when it gets a really high temperature, the block is going of concrete is going to expand, and that's going to be pushing against a block of another block of concrete. And if it doesn't have enough room to expand before it comes to a stop, then it's just going to cause the block that it has to break, or the block that it's against to break. And then you get, of course, a road repair that has to happen, and potholes and stuff like that sort. So what we've just figured out to do is we try to one thing is you can lay these things like railroad tracks and concrete pads and stuff like that. You can lay those down in the hottest of the day. Then they will come out to be about as long as you'd expect them. And then if it really is one of the hottest days of the year, very rarely will you get much hotter than that, but you still could. You will get much colder than that, and colder just is going to cause it contract, and it'll just leave a bigger hole between the adjacent spaces. So that's what they do, or that's what they did for a long time with train tracks. Is they would install them on the hottest days of the year. Which, by the way, laying train track is certainly one of the easiest, least sweat producing jobs you could ever imagine. So I'm sure those people are really happy about that. Now we do it such that they don't even have a seam. They're just basically a continuous piece of metal. And they still now, because of that, have to do it at the most extreme temperatures specifically for that reason. But you can see pictures of railroad tracks where they're going straight, and then all of a sudden they'll do like that. that's a matter of what we discovered by thinking about the atoms making up matter and the fact that they vibrate such that their kinetic energy is proportional to the temperature. That gives you the idea that their equilibrium distances increases with increasing temperature, and that gives us the idea that things expand upon increase in temperature and contract upon decrease in temperature. So what I'm going to do now is go ahead and give you an equation to use for that and tell you about some of the different things we could do for it. So for instance, if you're talking about the thermal expansion, one equation we can use, I think I want to go back to blue on this. So thermal expansion. What we'd say is that basically the thermal expansion, the amount of change in the length, which I'll call delta L, that delta L is directly proportional to, so that little alpha there that I drew, that's the symbol that we use to mean proportional to, which means basically if something's on the left and something's on the right and they're both in the numerator position, then they're thumbs up, or one's in the numerator and one's in the denominator, then they're thumbs down. Anybody know? Is that a student doing that that makes that, or is it just because I'm doing it? I just saw my screen like have fireworks behind it, so I don't know if that's something that students are doing, or if it's automatically doing to me because I did thumbs up, thumbs down, or thumbs up, or what. But anyways, if y'all know anything about Zoom, let me know. All right. So this change in length, what I say, is proportional to the original length. And it's proportional to that because I suspect you know that if you had a 3 centimeter piece of iron and you had a 3 mile piece of iron and you put them both out when they had a temperature of 20 degrees Celsius, and then you came back later and the temperature had reached 30 degrees Celsius, you would see the 3 centimeter piece of iron is a little bit longer. You might even, in fact, have to take veneer calipers to it to measure how much longer, but you'd see it's longer. But if you went to the 3 kilometer piece of metal, of iron or whatever, you'd see that that difference is quite noticeable. So bigger objects are going to increase by bigger amounts. So that's why I say the change in length is directly proportional to the original length, but it also should be directly proportional to the change in temperature. So physically speaking, that's the two things that really matter. And what goes into mathematics and of switching from a directly proportional to an actual equation is you need a constant. You need a equation to include a constant so that you can make it actually equal to. So what we did is, well, we know something else affects this length. So, for instance, we know iron goes at a different rate than does copper, and that goes at a different rate than, say, brass, or so on and so forth. So, what we decided to do is make that constant such that it is related to the property of the material. So, ultimately, what we do is we say delta L is equal to, and this is an unfortunate fact, but they use the symbol alpha for the constant. Okay, so this constant is a constant in the sense that it's some number, but it's also not a constant in that it depends on what material you're talking about. So we'll say this times L0 times delta T, and this is called the coefficient of linear expansion. So I'll just break it off there. That's really the equation that we need, to be honest with you. You don't need any more, but that's not generally what the textbook has you use. So I'll show you, and this is the whole reason I derived this, I'll show you exactly what most people use and where it comes from. So delta L is actually L final minus L initial. And then you've got alpha L0 delta T. So I can then pull the L0 on the other side, and I'll get L final is equal to L0 plus alpha L0 delta T. And then you can see I got a common factor of L0. So ultimately, I can write L is equal to L0 times 1 plus alpha delta T. And that's the equation that more people use than the other one. But to be honest with you, I always like the original one with the red box that I drew up top where I explained what the coefficient of linear expansion is, because that's one I can come up with just thinking about the physics of it. Okay, I don't have to do anything beyond doing the physics of it, and I can come up with the answer. And if I need this form, I can derive it from it. So that's what that is. There's actually a nice table in your book. It's table 17.1. So what I'll do is say C table 17.1 for coefficients of expansion. And it has ones like aluminum, brass, copper, so on and so forth. So for instance, just as an example, the coefficient of linear expansion for aluminum is 25 times 10 to the negative 6. Now, if you look at this, you realize this equation, the second one I wrote, you realize that the number 1 has to be added to alpha times delta T. Well, delta T will be measured in Celsius degrees. Remember, we subtract, so that ends up becoming Celsius degree as opposed to degree Celsius. So in order for you to multiply alpha by delta T and then add it to a pure number 1, alpha must have the opposite units that the delta T does, or the reciprocal units. So that tells us the units of alpha are Celsius degrees to the negative 1 power. So that's what aluminum is. If you want to look at brass, brass has a value of 19 times 10 to the negative 6 Celsius degrees to the negative 1 power. Some extremes are more common ones that are helpful, and a couple of them are rare, very important. The coefficient of linear expansion for iron or steel is essentially 12 times 10 to the negative 6 Celsius degrees to the negative 1 power. And here's another really important point. The alpha for concrete, but also for brick, that alpha is also approximately 12 times 10 to the negative 6. Can anybody guess why I think that's a big deal or something helpful?
Also, when you make rebar, it doesn't pull apart.
Exactly. Uh, Basically, there's a product that we use in building, especially in building big buildings, basically called reinforced concrete. And reinforced concrete is concrete that's been poured with steel in it. And also, like he says, you can lay rebar down when you go to pour concrete. You can lay not necessarily rebar, but there is a screen type steel mesh you put over when you hang or when you put up say stone on the wall or something like that. So those things are all going to expand and contract with different temperatures. If that's the case, if you're using steel and you're using these bricks and concrete together, if they had different coefficients of expansion, then they would slowly break apart and actually cause like the reinforced concrete to become rubble after a certain number of changes in temperature. So we lucked out in that nature gave us this wonderful thing where the coefficient of linear expansion of concrete block and steel are all about the same, and we can embed them in there without them vibrating loose due to differences. Even though there are small differences, but the differences are small enough where it doesn't harm you. It does sort of make the lifetime of reinforced concrete maybe finite, more so than we expect. But so far, we haven't run into many problems. I haven't read the literature from the American Society of Civil Engineers regarding that, but I suspect there probably is some end cap. I suspect, for instance, reinforced concrete maybe is not that good to last more than 100 years or so. I could be wrong, but I would think that over time, that little difference is still going to make a difference. But for right now, it's good. Another time that comes in handy is when you go to make a fill-in for a tooth. I'll get to you, Mark. When you make a filling for a tooth, you can imagine how bad that would be if you made a filling that had a different coefficient of expansion than the tooth itself. Because the first time you drink something hot like coffee, it would cause the filling to expand at a rate quicker, say, than the tooth did, and the tooth would explode, which is suboptimal at best. Anyways, Mark, go ahead. What's your question?
Yeah, I just wanted to ask, there's a problem on it's the second problem on the homework for this week.
Okay.
Um, and it looks very similar to this, except it's the change in volume and initial volume. And then they use beta instead of alpha. Is that
Yeah.
the
So if
same
you
thing,
think
or is this
about
we're talking different stuff here?
Yeah, no, it's literally almost the same equation. Sometimes when they deal with volume, there will be a negative issue that comes in there, meaning a negative sign that pops in. I'm going to pull the equation right now. So what they do for that one, just so you'll know, is you can do it for an area too, not just a volume, but you can say that delta V is equal to beta times, because there's no reason to suspect that the alpha and the beta would be the same for a given material. So they give it a number, another symbol beta, and that's going to be times V0 times delta T, which means you can get a V is equal to V0 uh, times 1 plus beta delta T, like that. So you can still get that same equation, but it turns out that beta turns out to be approximately 3 times alpha, which is kind of interesting because a volume is 3 dimensions and a length is 1 dimension. And it's almost as if you just multiply it times the length in this direction, and that direction. So yeah, that's the difference, is you use that.
Okay, thank you, Professor.
No problem. So yeah, these are important as well. They're really not that difficult. Sometimes you got to keep your wits about you. Like if you want to talk about solving a problem of filling a gas tank. So if you fill a gas tank, the tank is actually made of steel, but the volume inside is what is changing there. And when you fill it up with gas, in principle, the tank will have the air temperature, or maybe a little hotter because it's close enough to some of the giblets of the engine that get hot while they're running, depending on where the gas tank is, where the engine is, how close the gas tank is to the axle, and all that good stuff, and to the exhaust. But it's generally closer to air temperature. And the gas that you pull out of the ground is closer to ground temperature, so on the order of 50 degrees Fahrenheit. And you put that in, and then it's immediately the gasoline's going to start to heat up, and as the day goes by, both of them will start to heat up. Now, if you filled it all the way to the rim, and maybe you even did like my dad used to do, and probably still does, is my dad will go to the gas tank, he'll fill up his truck, and then he'll rock it back and forth, so he can get every little ounce. My dad's like me; he's probably a little bit obsessive compulsive. Well, I should say, I am a buttload obsessive compulsive, and I suspect my dad probably has the same leanings. I know he has some obsessive compulsive tendencies from some things, but I give him the benefit of the doubt. But the main thing is he does that and he fills up his tank. Well, that could be a problem if you do it and then everything gets hotter, because if everything's going to get hotter, does the gas expand more rapidly than does the container? If it did, that's going to build up a high pressure inside the tank. It might even be a high enough pressure to pop the lid off. God only knows what else. So that's a big issue. So when you go to analyze that one, it's a little bit problematic, because you got to think as the volume uh, as if it were one solid chunk of steel that now has been evacuated out of just a shell of steel. And that's actually how the thing that's inside is going to behave. That's a common problem students don't necessarily get. So one of the fundamental rules we talk about with linear expansion is, if you have a plate like this, and let's say it's not even a plate, let's go ahead and make a 3-dimensional thing. If I heat it up, what's going to happen is that plate is going to expand in that dimension. So it's going to get a little bigger this way. And now maybe it looks like this was 4 units over. And then this one that was originally here, that's going to expand a little bit as well. So it's going to be here. And then thirdly, this one that was back here is now going to expand a little bit as well. And it's going to be back here. Like that. So that's how the expansion goes. What we're saying here is every dimension is going to increase. That's the nature of this expansion. Every dimension will increase. So then if I ask you this question, here's a plate of steel and here's a hole where we cut out of that plate of steel. And what I want to know is when this gets heated up, how big will it be? In other words, does the hole get bigger or smaller? And I mean from heating. Anybody know the answer to that?
I'm gonna guess it stays the same.
That's actually a pretty good guess because it at least requires you to go that second iteration of thought. Actually, what happens with it is it acts just like the piece of metal that you cut out of it. Okay, and that's the parallel I was trying to make with the gas tank versus the a chunk of iron that they sort of hollowed out the center of to get rid of the chunk. So it turns out that circle will actually get bigger as well. Because we know that if we cut a circular disc of steel and then we heat it up, its diameter is going to get bigger. So the whole thing gets bigger. And that's exactly how that hole in there is going to behave. Because
Professor, are we talking? Sorry, Professor. Are we talking about like by the thermal expansion of the air? Because that's what that's what it's contained.
oh no, it's just the way the thermal expansion of the metal works as well. The air would do that too, by the way. What I think what Jerry's getting at is, am I arguing that the air, because we heated up everything, the air got a little hotter, so it's going to expand as well, and that's going to cause the hole to get bigger? In principle, that could possibly happen, but really, even if we did this in a vacuum, if you heated up a chunk of metal with a hole in the middle, the hole would get larger as well. Does that make sense, Jerry?
I take your word for it. I kind of can't wrap my mind about how. I mean, the outside I could see expanding, and I could see the inside being pushed in. You know what I mean? Because
Right.
the metal is expanding, but I can't wrap my hand around how it gets bigger in the inside.
I'm 100% with you. I didn't believe it at all. But if I was in my actual classroom as opposed to my boring little house here, I have a wonderful demonstration that convinced me, and I'll just tell you about it. And when we get a chance, I'll show you it again. But in the physics classroom, I have access to this. So let me stop sharing a second and let me look at you. So we have a brass little ball like this that's got a piece of metal threaded into it and a handle on the end. And then we have another handle with a little piece of brass sticking out of it. And in that case, there's a toroidal ring on the end that's just big enough for this, or almost big enough for this to slip in. When we heat the two up, though, what we find is if I heat up the donut shaped ring, then all of a sudden the ball will fit through it, whereas it wouldn't fit through it before. So that was what I finally saw in reality happen to make me convinced that it would work that way too. Because I was like you, it's like every dimension is going to expand. So why wouldn't the atoms around the edge of the circle push in? It turns out they just don't do that. And I think the explanation of what to think of it is part of the reason that it does it. If this was in fact a sheet of metal without a hole in it, you could slowly take and maybe etch a little, let's say something with the sharpness of a knitting needle, or not even knitting needle, a actual sewing needle, and you could etch a circle just barely on one side of that plate, and then you heat it up, and you'd see that the middle circle inside of that etching would get bigger, and you do it again after a few more etchings, so it's getting thinner, it's still getting bigger, and you could slowly adjust it by adding more and more etchings until eventually it becomes two separate pieces of metal. And the fact that you can do that continuously by making the cut slower and slower and slower tells me that probably that is the reason that it behaves just like the atoms next to it are expanding, even though it doesn't have an atom next to it anymore on the inside. Okay. Hopefully that'll help you. That is the kind of problems that they will be asking you about, though, for instance. So we have the volume expansion. Uh, then we have this really weird temperature of water. The water profile is quite odd. I'm going to go ahead and share my screen again. So there's something odd about water. And like I said, it's not the only element or compound that does this, but it is a very important element or compound, and it does do it. And because of its importance, it's allowed us to have life through ice ages and stuff of that sort. So that's kind of nice. Uh, I'm trying to find. There you go. Okay. So your book actually has these graphs, so I'm going to go ahead and show them to you. First off, I'm going to draw a volume versus temperature graph. That's the volume. And that's the temperature. And if you did this for water, what you would get is basically a graph like that. And this would correspond to 4 degrees Celsius. This would correspond to 0 degrees Celsius. And this is volume of 1.000000 grams of H2O. Okay. And what we'd find is that at 0 degrees Celsius, it is 1.00013 cubic centimeters. So this is measured in cubic centimeters in cc's. So that's what the volume would be there. And in fact, the volume right here would be 1.00000. So the maximal or the minimal volume happens at 4 degrees Celsius. If you go on, of course, to 5 degrees Celsius and so on up to 100 degrees Celsius. Whoa, did not mean to do that. But I can do something with that. That would be mighty helpful. Okay, if I came up here and looked at that, that value would in fact be 1.04343 cubic centimeters. So you can see the density of water changes and all that good stuff over temperature, just like I was telling you earlier. We grabbed the temperature for copper at 20 degrees Celsius, but it would be different at, say, 25 degrees Celsius. Or as you can see, the density of water is 1 gram per cubic centimeter, 1 kilogram per liter, or 1,000 kilograms per cubic meter. Well, it turns out water has quite a bit of range. It's going to change quite a bit from that 20 degrees Celsius. It's going to go to a volume of 1 cubic centimeter at for 1 gram at 4 degrees Celsius. But when you go up higher, it's going to be 1.04 cubic centimeters per gram. Okay, so that's kind of neat. Another way of looking at it, though, is to look at the density of water. And that's what I'm going to do now. I'm going to do another graph. And that graph will be So now I'm going to say this again is temperature, but this time it's the density of water in grams per cubic centimeter, which is also called the CC. So that's why man, it really hurts when I try to correct my writing. So I'm going to say gram per CC because it's easier to write. In this case, what you see is the density at 0 degrees Celsius is low, and then it gets its highest right at 4 degrees Celsius, and then it comes back over here. So this corresponds to 4 degrees Celsius. And in this case, the density is quite low. This is 0 degrees Celsius. The density is 0.999. I'm going to go with 97, something like that. And this density up here, of course, is the 4 degrees Celsius. That's the 1.00000, and so on and so forth. So that anomalous behavior is actually helpful, because if you imagine how a lake or a pond or the Great Lakes might freeze, what happens is the air temperature gets really cold. The ground temperature gets cold, but it's not going to get that cold because the ground temperature's got a huge amount of ground. It's literally a heat sink. So as more and more energy flows out of the ground to the colder air, there's a butt ton of energy below. So the ground stays roughly the same temperature, usually on the order of 50 degrees, something like that. But when the air is getting colder and colder and colder, the water gives up some of its temperature to the air, gives up some of its heat to the air, and drops its temperature. And then that lower temperature, if you look at it on a density scale, let's say we're going from 10 degrees Celsius to a lower, you can see the density goes up. So if you look on the graph right here, this could be, for instance, 10 degrees Celsius, and this would be, say, 9 degrees Celsius. You'd see that the density actually goes up when you go from high temperature to low temperature over here. So guess what? You've just cooled that surface water temperature, which may have been 10 degrees Celsius, to 8 degrees Celsius. That particular temperature of water has a higher density than the stuff below it, which is even colder. So it falls down. And then the next part gets cold again, and then that falls down, and the next part gets cold again, and that falls down. And he keeps doing that over and over and over again until basically the most dense part occurs at the very bottom. That, like salad dressing, the oil and the vinegar and all that stuff separates out when you leave it in your refrigerator for a period of time. And oil being lighter than water and lighter than, therefore, vinegar, the vinegar will be at the bottom and the oils will be floating on top. Same thing happens with this. Slowly, all those different temperatures of water have aligned themselves so that the most dense stuff is at the very bottom. A little bit higher is a little less dense, a little bit higher is a little less dense. So lo and behold, the lowest temperature, or excuse me, the highest density occurs at the temperature of 4 degrees Celsius. So that means if Lake Erie literally froze completely over, you could say without a doubt the temperature of the very bottom is about 4 degrees Celsius, and that's it. Right? No matter how much time it had, the most dense water is going to occur at 4 degrees Celsius, and you're going to find that down around the bottom. So hopefully that'll help you better understand what we're talking about here. But because of that, you're never going to get a body of water of any appreciable depth, touching the land. You're never going to get that to freeze solid. Obviously, the reason why I'm putting all these caveats is you probably have an ice maker or a ice tray. You've probably seen that in your life. So obviously, if you pour water in one of those things, you can get the whole part to freeze, right? But it's a little different when you start talking about depth subjected to air and so on and so forth. Now, not only that, but also once it freezes over, notice you now have, in addition to the water, which has got a high coefficient of, has a high specific heat, you now have a piece of ice over top of it, which is a fairly decent insulator and is going to protect the water from getting colder still. So all of that spells that we're not all going to die during a ice age. Anybody have any questions on that?
Just a quick question about when you stand past 0 degrees, you just extrapolate the curves. Does the density just keep as it goes to -10, -15, like you're in Antarctica? Is that ice down there less dense than zero? Like,
Uh,
uh,
we do know this is ice. That ice and water is another weird thing in that your ice floats in your iced tea. So what we know is ice is less dense than water. So once it hits that 0 degree mark, it does continue to decrease. Uh, I don't know that it decreases at the same rate, but we do have that data. In fact, we have specifically the specific heat is the slope of the graph of temperature versus heat. So you could actually make the graph based on those specific heats of ice, and we have specific heat of ice for 0 degrees Celsius. We have specific heat of ice of -10. We have a different specific heat of ice at -20 degrees Celsius. So yeah, they do continue to do that. Last I checked, I never saw any way where it turned back on. It seemed to be a straight linear interpolation with ice. But I would be curious to find out if it ever did, something more than just straight linear. I just know the only part that is linear definitely is this part right here, right around 4 degrees Celsius. That help you? So yeah, if you want to find out more about that, definitely Google specific heat of ice at various temperatures. That's the word is specific, SPECIFIC. We haven't covered that in the class yet. You might have had it in other classes, but it's a symbol C, and it tells you basically the amount of heat that has to be absorbed to change the temperature by 1 Celsius degree for a given gram or a given kilogram, depending on which units you're using. All right, anybody else have any questions? All right, your book covers section 17.5, which I find super interesting from an engineering standpoint, but I'm not going to cover that. So I'm going to write right here, we skip subsection 17-5, which is thermal stresses. So this is one of the really more important calculations for an engineer, but physicists don't use it that much. And that's probably why I find it so interesting, because it's, not something I use all the time. But in general, what they're finding is that the pressure, so I'm going to put the actual results of here, the pressure, which is force divided by area due to thermal stress, turns out to be equal to alpha, which is the coefficient of linear expansion, times E, which is called Young's modulus, times delta T. So let me label this. This is called Young's modulus. And actually, I always get in trouble doing that. So that's called Young's modulus. And this is the linear coefficient that we just learned about. Okay. So what this is telling us is that, for instance, if you have a sheet of ice, let's say in like what I call a boat basin or a docking area, so a big rectangular segment of water, if that big rectangular segment of water gets cold enough to freeze, then it's going to have a sheet of ice across the top of it. And if the rectangular boundaries are a bulkhead, and a bulkhead, basically a dock, if you will, but those of us that live near the water know the bulkhead's the thing that keeps the land from washing away. What you want to know is, hey, is that ice powerful enough to rip up my bulkhead or to break my bulkhead? And that's the calculation that tells you it. Okay. So that's kind of neat. It literally tells you how much pressure is going to be applied to that. Then you can look up the breaking strength or the ultimate strength of whatever bulkhead you use. A lot of people, at least the bulkheads that I've built in my life, I always use just one by material, 2 layers deep with tar paper between them. But that's basically what we always used. And I can look up in the Wood Forest Products Association release manual, I can look up what the ultimate strength of that type of wood is. And if the pressure that I get from this calculation is larger than that ultimate strength, that means the ice is going to literally crack through the bulkhead. Now, that you do not see that often, because normally it's got that and then it's got dirt filled back behind it. But sometimes people go on the cheap and don't pay for the dirt, and then you have nothing but air behind it, because all they really worry about is that it don't fall out, not that it doesn't fall in. In that case, what you see happens is the ice will literally fill that whole space. And then when tide comes up, the tide will force that ice to lift the bulkhead out of the water. That happens a lot. I've seen it a lot of times. You'll see bulkheads and they'll go like this, and it's not the old train track scenario. It's actually quite worse. All right. Any questions on that? We did skip it, and like I said, I don't think I have any homework problems like it in the homework set. If you do, let me know. I'm not going to mark off points for it, and I'll try to take it out at least for next time. But I think I got rid of all of them in the practice test as well as in the homeworks. But you're not required to do that. The very next thing we want to talk about is the ideal gas laws and how to use them. So the ideal gas laws, and this is where in chapter 1, your book talked about laws versus theories versus hypotheses and stuff like that. Well, they were originally discovered in many ways. And for instance, the golden rule for scuba diving. Does anybody know? Anybody have a scuba diving certification? Because they might be able to tell me which physics law is the most important to physicists. I mean, to scuba divers. Anybody know?
Is it Boyle's law?
It is Boyle's law. Yes. So Boyle's law is the other one. One of the things they, for instance, tell you is the golden rule of scuba diving is never hold your breath, never hold your breath, never hold your breath. Right. And that's exactly right. And that's because Boyle's law says that pressure times volume is equal to a constant. And that goes on the assumption that temperature is constant. And grams or mass is constant. In other words, you're not letting more gas in or out. So I'll say mass is also a constant. So when you combine all that, what you end up seeing is P is equal to some constant over V. And notice the P and the V are on opposite sides of the equal, and they're on opposite sides of the fraction bar. So that's what I call thumbs up, thumbs down. So thumbs up, thumbs down. That means if the volume goes up, that must be a result of the pressure going down. Or if the pressure goes up, the volume must go down. So why does that work in scuba diving? Well, guess what? When you go below the surface of the water, at the surface of the water, you're at usually 1 atmosphere of pressure, which is about 14.7 pounds per square inch. It's also 1.01 times 10 to the 5th pascals, which is 1.01 times 10 to the 5th newtons per square meter. But as you go down below the surface, you're increasing the pressure based on the density of water now instead of the density of air. You're not adding any more air above you, you're adding water above you. And in fact, by the time you get to 33 feet, you've increased the pressure from 1 atmosphere to 2 atmospheres. And once you get to 66 feet, you've increased it to 3 atmospheres, and then 99 is 4, and 120 is 5, and so on and so forth. It's 125 or whatever. So that's a really big deal. So when you're down underwater, you're at a high pressure. And if you go to ascend to the surface, if you happen to hold your breath, what's going to happen is the volume of your lung has a limit. Okay. You don't always, when you take in a breath, you don't necessarily fill your entire lungs with air. So there's a little bit of play. So in principle, you can swim up, a foot or so and nothing would happen. But if you did hold your breath and you raised yourself up substantial, a little bit more than a foot, it starts to get dangerous really quickly. Like literally, if you have something wrong with you, a foot might be enough to screw it up. But what's going to happen is as you ascend, the pressure on the outside of your body is decreasing, decreasing, decreasing. So the volume of your lung is going to expand, expand, expand until it reaches its maximum. And guess what? It's not going to stop there. It's going to pop. And when it pops at the alveoli level. It pops at the actual outer lung level, and you get what's called an arterial gas embolism. That bubble of air can go in and go into your brain and cause like a clot, all sorts of bad stuff. But Boyle was the one that discovered this sometime in the 1600s, and basically that's a fact. We know that when you increase the pressure on a closed container of gas, it will decrease its volume and vice versa. So in that sense, it's a law that it always applies. So that's a good reason for calling it a law. It's also historically called a law. So that's another good reason for calling it a law. Now, there's also another or several other ones. There's other laws that have been discovered over time. And for instance, one of them is Charles's law. So Charles's law, oops. Charles. Yeah, it's a British thing. So Charles's law says that pressure is directly proportional to temperature. And again, this assumes that the missing variable V and M are constant. So what we mean by that is if you take a balloon, for instance, that you blow up and you bring it over to a fireplace where you got a fire going and you leave it there, when you come back a little time later, what you'll see is that the balloon got bigger. Now, this is a little different than Charles's law because it got bigger means its volume got larger. But the reason it got bigger was that the pressure inside became larger because the temperature became larger. Because that pressure inside was larger, that forced the balloon to stretch more, and therefore the volume got larger. But that's what Charles's law says, and Charles's law was found in the early 18 to mid 1800s. So that's one of. Oh, excuse me, I mixed it up. That's V and T. So actually, the example was right directly. Sorry about that. Let's change this P to a V, everybody. I just looked on your book at the last second and saw P versus T and didn't realize it was with the other category. I just assumed I had misremembered which one was which. So yeah, that's V versus T. So yeah, a balloon does get a larger volume with higher temperature. And then there's Gay-Lussac's law, which I never remember, and that's the whole reason I always look it up. Lussac apostrophe S law. So Gay-Lussac's law, basically, he was around the 1800s as well. That says pressure is proportional to temperature. And back on the other one now, since volume's part of it, I've got to erase this volume and say volume and temperature. I say pressure and mass are constant. And this one, of course, corresponds to volume and mass are constants. So those are all fundamental laws in the sense that any experimentalist today will find those exact same things to be true. Now, once it goes a little further than that, we can start to put things together. And what we see is that P is proportional to T, and V is proportional to T, and P times V is proportional to a constant. So we might reach the conclusion that P times V is equal to T times some constant. But we also know that that constant, since we've now taken into consideration all the variables but the mass, we know this constant depends on mass. in some way. And in fact, it's probably reasonable for you to think that if I put a buttload of more atoms into the collection, that's going to cause the pressure to go up or the volume to go up, right? So you'd expect something proportional to the number of atoms or something proportional to the amount of mass to be on the right hand side with the T. So ultimately what was done is we say PV is equal to N times R times T, and this is called the ideal gas constant. Now, be advised, if you're going into engineering, they do this entirely differently. So what they have in engineering is they don't have an ideal gas constant. They sort of do, but they have an ideal gas constant that is constant for each element or each compound. So it's a little weird. So what they end up doing is they end up absorbing the R that we use. They absorb into that the molecular weight so that it automatically basically converts the mass to moles. And this N right here is number of moles. Okay. This temperature must be in Kelvin. And this volume can be in a lot of different things, as well as this pressure can be in a lot of different things. And what dictates that is what value of R we're using. So I'm getting ready to give you the various values of R. So the various values of R, the one I use most often is 8.314 joules per mole Kelvin. Another one that comes in handy is 0.0821, and that one's liters times atmospheres. So that's using a pressure unit of atmosphere. And then that's divided by moles times Kelvin. And then another version is 1.99. And in this case, it's calories, lowercase calories per mole Kelvin. So you can see if you're using 8.314, what you'd want to use for volume is cubic meters. So I'd say implies V equals cubic meters and P equals pascals or newtons per square meter. Okay, so that's what you use when you're using that gas constant. If you use liters for the volume, and you use atmospheres for the pressure, then you can use that constant. And this one with calories is quite a bit different. And I want to say you're going to use the units of volume should be, I think, cubic centimeters. I have to double check on that. I never use the 1.99, but I think a lot of chemists use that a lot more often. But looking at the units, I don't see any way it would work out otherwise, just because calories are normally part of the CGS system or something like that. So actually, rather than putting that, let me go ahead and erase it, and I'll leave it up to you guys to look it up before you use that. And before we meet next time, I'll make sure I have a definitive answer on that. It says it somewhere in here. It's just a matter of whether I remembered it or not. So how do you actually solve problems with this? Well, let's solve one of the world's simplest. Yes, go ahead, Mark. Sorry.
Professor, can I ask you a quick question before you move
Yes.
on? For R, you said you're pretty much constantly using that one, or if you don't, will it be given some way?
Yes. So what I've done to date is I took a photograph of the inside front cover of Giancoli and the inside back cover of Giancoli, and I include that in every test It's normally like down the last question or something like that, but it's not really a question. It's just where all those constants are. So it has all your conversion factors as well as your gas constants and all that stuff.
Does that include that number you talked about in the first part of your lecture today?
Yeah, the 1.6605 times 10 to the negative
Yep.
27th.
Yeah.
Yeah, it includes that as well.
Sweet.
In fact, I should probably show y'all that. What I'll do is I'll try to remember to post the picture so y'all will have it. When you're doing your own homework, you can just use it and refer back to it in case you need anything. That way you'll feel a little bit more comfort when you start actually taking a face-to-face test and have to use it. You'll know where everything is. Okay. Another
good.
thing I got to tell you about the gas law is this pressure has to be absolute pressure. I want to do this in blue. And what I mean by absolute pressure, for instance, if I go out to my truck and put the pressure gauge on my tire, it's going to read like 45 psi. What that 45 psi is basically I'm sticking this pressure gauge on it that pushes the little tongue sticking out of the nozzle. It pushes it in, which gives the air inside of the tire free access to the chamber inside of the pressure measuring device. That pushes that little white stick out like a piston. What it's pushing against, though, is atmospheric pressure. So what's happening there is the pressure of the air inside the tire is fighting the pressure of the air in the atmosphere. So what I'm getting is what's called gauge pressure. It's gauge pressure is the pressure minus 1 atmosphere, whereas we need the absolute pressure. So in that case, the absolute pressure of the tire would be 45 psi plus 14.7 psi. So with that in mind, let me give you those constants as well, just so you'll get used to it. So P atmosphere is 1.01 times 10 to the 5th newtons per square meter, which is 1.01 times 10 to the 5th Pascal, which is about 14.7 psi. So that's pounds per square inch. It's also equal to 1 atmosphere, which is another unit of pressure. Okay, the atmosphere was the one I was using when I was talking about scuba diving, and it's just because it's a very convenient unit. But that's what we use for atmospheric pressure. So you got to make sure you're using absolute pressure, not gauge pressure. But using it in general is really not hard. So a typical example of an ideal gas problem is what is the volume of 1 mole of an ideal gas at standard temperature and pressure. Okay. You might misremember this, like I often do. Standard temperature and pressure literally means 0 degrees Celsius and 1 atmosphere. So it doesn't mean 20. I always want to think it does because that seems much more reasonable, but it doesn't. It wants to use 0. So here's the answer. So PV equals nRT gives me V is equal to nRT over P. So V is going to be equal to 1 mole times 8.314 joules per mole Kelvin. And then times temperature, which is 273.15 Kelvin, carrying way more sig figs than necessary. And then 1.01 times 10 to the 5th pascals is the pressure. So if I do this, it comes out to like 24.3. It's a fairly famous number. So I'm going to go 1 times 8.314 times 273.15. And then I'm going to divide all that by 1.01 times 10 to the 5th Pascal. And I get 0.02248, hearing one extra sig fig. Now, if you look at these units, what I see is a joule is a Newton meter. So a joule is equal to a Newton meter, which equals a kilogram meter squared per second squared. A Pascal is equal to a Newton per square meter. So you can see that this, for instance, square meter down here matches with the square meter up top and gives you a meter to the 4th power, right? But when you take into account that the Newton is going to cancel out a bunch of that, then you're a little better off, because you can now say this is, oh, sorry. I'm going to say this is equal to kilogram. Now it's supposed to be kilogram meter per second squared. So I'm dividing this by a meter. So it's kilogram per meter second squared. Now the meter is actually, the meter is actually on the bottom like it was before. That means it's going to come to the top. That gives me a meter cubed in the top. This second squared cancels out with that second squared. This Kelvin cancels out with that Kelvin, and this mole cancels out with this mole. So we know that the units are square cubic meters. Sorry about that. That's what the units are there. We also know that a milliliter is, or excuse me, a liter is 1,000 cubic centimeters. So we could do that. We could also figure out that this, in fact, is a cubic meter is equal to 1,000 liters. Therefore, we can say it's 22.48 liters is what 1 mole of an ideal gas at standard temperature and pressure occupies. Okay, so that's just a rule that we're supposed to know. And it's just a handy figure to use from time to time to time. But it also is helpful to be able to switch back and forth between liters, cubic meters, and cubic centimeters. But that's just one simple problem to work. I will remind you that as long as you have a fixed number of moles or a fixed mass of gases, then you could say PV over T is equal to N times R. So if the mass or the number of moles is constant, then that means P1 V1 over T1 is equal to P2 V2 over T2. That's a way that we use the ideal gas law without actually technically using the ideal gas law. This is sort of just using Boyle's, Charles's, and Gay-Lussac's laws. But if you know those, 3 of those conditions in one case and 2 of those conditions in the other case, then you can figure out the third. And of course, if the temperature is constant, then it's just P1 V1 equals P2 V2. Or if the volume's constant, it's P1 over T1 is equal to P2 over T2. So all of those different things are ways that you can apply the ideal gas law. We mostly go on the assumption that you have some experience with it. I will leave the rest of the examples up to you, but I'll also be willing to answer questions. And I definitely want you to look at my YouTube channel and any videos you can find if you need any more help, or just send me a text message or an email and I'll help you. We're actually done with this chapter. As I told you, I was trying to cover the main topics. I haven't worked hardly any problems, to be honest with you, and that's fine because I don't think it's too terribly bad. But I'll definitely be making some videos in addition to the ones I've already made, and they'll help you more. When I actually make ones that are relevant to this chapter, if I make any in the next couple weeks, I'll definitely let you know so that they're on YouTube. On my YouTube channel, and I'll even post them on our Canvas page, so you'll have a little bit more experience. Hopefully, I'll do more before Sunday. Now, you guys are free to go, and class is over, and I will see you next week. I will tell you, I'm going to move the homework. I'm going to let you guys turn it in on Wednesday, just in case y'all need a little bit more time to find examples. So it'll be due Tuesday night instead of Sunday night.
All right. Thank you, Mr. Younger. Have a good one.
You're welcome. You too. See you, Elijah.
Good one, Mr. Younger.
Professor, I came in like 5 minutes late. Do you have me for attendance?
Yes. Yeah. I have a log that keeps track of who signs in, so that's good.
Okay, thanks a lot.
No
See you
problem.
later.
See you, Gary.
Professor, on that note, I should probably tell you for
Yes.
today's lab and today's class, I've been with Justin Riddick. He's been online with me. He's here.
Okay, yeah, definitely that helps me. So Justin Riddick has been there. Let me write that down real quick before.
Yeah, we both live near each other, so he just came by.
That's no problem. I don't really take off points for attendance or anything like that. I just like to know in case I need to drop someone because they've stopped attending and they could actually possibly get a refund and that sort of thing.
Okay, thank you, Professor.
You're welcome. Aaron's asking, where do I find the class code? The people at Pearson have advised me never, ever, 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 ever give the class code. And here's the reason. The way I do my Pearson course is I do what they call a deep integration. So the grades automatically come to my grade book. If you need the class code, that's usually because you're trying to access Pearson from the internet instead of from Canvas. So if you just click on a homework assignment within our Canvas page, it will take you to the appropriate Pearson course because it's linked to that one. If I gave you the class code, you could go from the internet and do it, and then I'd never see your grades. And it just is always going to be that way. So that's why I don't give you the class code. Just know that all you have to do is click on chapter 01 HW in module 1. And that's where it'll actually ask you for the access key, or it'll allow you to buy one or whatever, or do the 2-week trial. Hope that helps you, Aaron. Let me know if you have any problems. This is a good thing to text me about if you're having problems as opposed to waiting for an email.
Have a nice day.
You too, Elizabeth. Nice seeing you again.
Nice to see you too. Bye.
Bye-bye.